sun is preparing to betray us. For centuries, we have looked up at our star and seen a symbol of constancy, a warm, reliable engine that dictates the seasons, grows our food, and anchors the mechanics of our solar system. We built our entire modern civilization under the assumption that the sun is stable. Our power grids, our global communications, our GPS networks, every piece of infrastructure that keeps the 21st century running is strung across the Earth, completely exposed to the vacuum of space, protected only by the invisible, fragile shield of our planet's magnetic field. We thought we were safe. We thought the sun was going to sleep. To understand why we felt so secure, you have to understand the rhythm of our star. The sun does not burn evenly. It operates on an 11-year cycle of magnetic activity. These cycles are driven by the complex churning plasma deep within the solar interior, causing the sun's magnetic field to twist, tangle, and eventually flip completely. We track these cycles by counting sunspots, the dark, relatively cool regions on the solar surface where the magnetic field is intensely concentrated. More sunspots mean a more active, violent sun. Fewer sunspots mean a quiet sun. The cycle that ended in 2019, known as Solar Cycle 24, was one of the weakest in recorded history. The sun was eerily quiet. It produced very few significant solar flares and almost no major geomagnetic storms. When the official NASA and NOAA prediction panel convened to forecast the next cycle, Solar Cycle 25, they looked at the data and reached a comforting consensus. Dr. Lisa Upton, a solar physicist then at Space Systems Research Corporation and co-chair of the prediction panel, helped present an official forecast that called for another exceptionally weak cycle, estimating a peak of roughly 115 sunspots by July 2025. The scientific consensus was clear. Humanity had been granted a reprieve. We were entering a prolonged period of solar minimum. The grid was safe. The satellites were safe. The sleeping giant was going to stay asleep. But here's the catch. The prediction significantly underestimated what was coming. Almost immediately after Solar Cycle 25 began, the sun started breaking the models. The sunspot counts did not gently rise according to the forecast. They exploded upward, shattering the predicted curve. By 2023, the sun was routinely producing double the number of sunspots anticipated by the official models. By October 2024, when NOAA and NASA officially declared solar maximum, the smooth sunspot count had reached approximately 161, roughly 40% above the predicted peak of 115, and arrived 9 months earlier than forecast. The sleeping giant had not only woken up, it was thrashing. The quiet, predictable star we thought we understood was suddenly littered with massive, complex sunspot groups, some of them stretching hundreds of thousands of kilometers across the solar surface. These were not just dark blemishes, they were loaded weapons. The magnetic architecture of the sun was becoming increasingly tangled, storing immense amounts of kinetic energy, ready to snap. We had built our modern world during a lucky temporary lull in solar activity, and now the lull was over. The sun was loading, and our technology was sitting directly in the line of fire. To comprehend the danger we are currently facing, we have to look at the mechanics of a solar eruption. The violence begins with the magnetic field lines. Unlike Earth, the sun is not a solid object. It is a rotating sphere of superheated plasma. The equator spins much faster than the poles. Over the course of the 11-year cycle, this differential rotation catches the sun's magnetic field lines and drags them, wrapping them tighter and tighter around the stellar core. Think of twisting a thick rubber band between your fingers. At first it just coils, but as you keep twisting, the tension builds. The rubber contorts into jagged, unstable knots. Eventually, the structural integrity fails, and the band violently snaps back to its original shape, releasing all that stored kinetic energy at once. On the sun, this process is called magnetic reconnection. When those magnetic knots finally snap, the resulting explosion is a solar flare. The plasma in the immediate vicinity is heated to tens of millions of degrees Celsius in seconds. It produces a blinding flash of electromagnetic radiation, X-rays, and extreme ultraviolet light that slams into Earth's atmosphere in exactly 8 minutes. But the flare is just the flash of the muzzle. The true danger is the bullet that follows. That bullet is a coronal mass ejection. When the magnetic field snaps, it can violently rip a massive chunk of the sun's outer atmosphere, the corona, and launch it into the void. We are talking about billions of tons of magnetized plasma, accelerating to speeds of nearly 3,000 kilometers per second. That's not the scariest part. The scariest part is that this newly awakened sun is already firing these weapons with terrifying frequency, and we have only narrowly avoided a direct impact. In May 2024, the Solar Dynamics Observatory, a NASA mission that stares continuously at the sun, watched an absolute monster emerge on the solar surface. It was cataloged as Active Region 3664, a sunspot group so large and so unstable that scientists immediately drew comparisons to the most destructive solar event in recorded history. This massive sunspot group was staggering in scale. It stretched nearly 200,000 kilometers across, wide enough to swallow 15 Earths side by side, and it was highly unstable. For over a week, it battered our planet with a barrage of high-energy flares, peaking with a massive X 8.7 class eruption. It triggered the most intense geomagnetic storms we had seen in 2 decades. The auroras were pushed incredibly far south, lighting up the skies in places that rarely see them. It was a spectacular light show for the public, but for the scientists monitoring the telemetry of our satellite networks, it was a harrowing stress test. But the massive sunspot group was not finished. As the sun's rotation carried it around to the far side, facing away from Earth, the tension finally gave way completely. We could not see it from our planet, but the joint ESA and NASA Solar Orbiter mission was perfectly positioned in deep space to witness the detonation. On May 20th, 2024, the sunspot group unleashed an estimated X 16.5 class superflare, a terrifying release of energy, a massive wall of superheated plasma, a direct hit that we completely dodged only because we were on the wrong side of the calendar. If that eruption had occurred just 1 week earlier, when the sunspot group was dead center on the Earth-facing disk, the X 16.5 flare and the resulting coronal mass ejection would have slammed directly into our planet. The resulting geomagnetic storm would have severely tested the limits of our electrical infrastructure. We avoided a catastrophic strike purely by the blind luck of orbital mechanics. But luck is not a new strategy. We have been surviving on it for 165 years. On September 1st, 1859, a British amateur astronomer named Richard Carrington sat at his telescope in Red Hill, Surrey, sketching a cluster of sunspots when 2 intensely bright beads of white light erupted from the solar surface directly in front of him. He called for a witness, sketched what he saw, and noted the time. His magnetic instruments swung off their scales within minutes. 17 hours later, the shockwave arrived. What followed was the most powerful geomagnetic storm in recorded history. The aurora borealis was visible as far south as Cuba, the Caribbean, and Hawaii. Gold miners in the Rocky Mountains woke at midnight, believing it was dawn. Telegraph wires across the United States erupted in sparks. The geomagnetically induced current was so intense that telegraph operators could disconnect their batteries entirely and continue transmitting on nothing but the energy delivered from the sky. Some telegraph paper caught fire. The reason the 1859 Carrington event did not end civilization was not that the event was survivable. It was that there was almost no electrical civilization to end. The telegraph was the most advanced network technology humanity possessed. There were no power grids. There were no transformers. There were no satellites. In the 165 years since, we have built an electrical civilization of extraordinary complexity, strung it across every continent, and called the absence of another Carrington-level storm safety. We were not safe. We were lucky. And in May 2024, we were lucky again. To fully grasp what a direct hit from an extreme coronal mass ejection means for the civilization we have built since 1859, we have to look past the light show of the auroras and look at the physical grid that keeps our world alive. When a Carrington-level coronal mass ejection strikes Earth, the initial shockwave of solar plasma compresses our planet's magnetic field, pushing it violently backward. This sudden, violent warping of the magnetosphere acts exactly like a giant generator in the sky. In accordance with Faraday's law of induction, this moving magnetic field induces massive electrical currents in the upper atmosphere. But electricity always seeks the path of least resistance. It does not stay in the sky. It dives down into the Earth's surface, hunting for conductive materials. The path of least resistance on Earth is our electrical grid. Imagine you are standing in a major metropolitan control center on a Tuesday afternoon. Everything is functioning normally. Suddenly, millions of amps of geomagnetically induced current flood the long-distance transmission lines stretching across the continent. These lines were not designed to handle direct current from the sky. The grid is built for alternating current, carefully balanced at specific frequencies. The solar surge completely overwhelms this balance. The first casualties are the massive house-sized step-up transformers that anchor the grid. As the direct current floods their copper coils, the magnetic core of the transformer saturates. The copper instantly superheats, melting the internal insulation and triggering catastrophic failure. They do not just shut down. They physically melt, burn, and sometimes explode. Within 90 seconds of impact, vast sections of the North American grid, the European grid, and the Asian grid cascade into failure. You are standing in the control center, and the screens go black. The lights go out. What I find most difficult to accept about that is not the darkness. It is the system that would be needed to repair it. The factories that build replacement transformers run on the grid that would be destroyed. The supply chains that deliver those transformers depend on logistics coordinated by the satellites that would be blinded. The recovery depends entirely on the infrastructure the event would erase. We cannot simply flip a breaker to fix a melted transformer. They weigh hundreds of tons, they are custom built, and the global reserve supply is terrifyingly small. Replacing them takes months, if not years. We are talking about a scenario where entire nations lose electricity, clean water pumping, and refrigerated food supply for an extended period. But it is not just the power. The extreme radiation environment in the upper atmosphere has already expanded the ionosphere, increasing the aerodynamic drag on thousands of low Earth orbit satellites. GPS satellites lose their lock. Air traffic control systems go blind, forcing thousands of commercial flights to land without navigational aids, while the crews and passengers at cruising altitude are subjected to radiation doses high enough to pose severe, immediate medical risks. The global supply chain, which relies entirely on just-in-time logistics coordinated by satellite timing, shatters in hours. Let's pause here because this is the full picture. This is not a hypothetical doomsday scenario ripped from science fiction. This is the established, peer-reviewed consensus of what a Carrington event-class storm would do to our modern infrastructure. The sun peaked so early and so violently that researchers now pinpoint the period from mid-2025 through mid-2026 as a critical danger zone for severe Earth-directed space weather. The sun is armed, and we are in the deepest part of the storm. The threat of an unyielding solar storm extends far beyond our power lines. It directly threatens humanity's effort to expand back into deep space. And this is not a distant, theoretical problem. NASA's Artemis program, designed to return humans to the lunar surface, was already planning precisely this kind of mission during the most dangerous window of solar activity. The question of how to protect astronauts during the violent peak of solar cycle 25 was not theoretical. It was the central safety calculation for every mission profile beyond low Earth orbit. We thought we were sending them into a quiet sky. Instead, they are flying into a storm. If a major coronal mass ejection, or even a fast-moving stream of high-energy protons, were to erupt while a crew was in deep space, the consequences could be severe. Unlike the International Space Station, which orbits safely inside Earth's magnetic shield, a lunar mission has nowhere to hide. The highly charged particles unleashed by a solar superflare travel near the speed of light. They can punch right through the hull of a spacecraft. At high doses, this radiation can cause severe cellular damage, acute radiation sickness, and a massively increased risk of long-term cancer. NASA has developed emergency procedures where the Artemis crew would literally build a fort out of their supplies in the center of the cabin to increase the shielding thickness. But against an X-class superflare, it is a terrifying gamble. But we are not flying completely blind. To mitigate this risk, researchers have developed advanced forecasting models, analyzing nearly 50 years of X-ray and magnetic data and identifying hidden patterns in the solar cycle. Dr. Scott McIntosh, a solar physicist and former deputy director at the National Center for Atmospheric Research, led a team tracking the complex, overlapping rhythms of the sun's magnetic field to pinpoint windows of extreme danger with greater precision than any previous generation of scientists could manage. And here is the discomfort buried inside that progress. The same foundational framework that told us to expect a quiet solar cycle 25 failed by 40%. The models that gave us confident forecasts of 115 sunspots at peak delivered a sun producing 161. The tools we now rely on to predict individual flares within a cycle are built on the same foundational physics as the models that failed to forecast the cycle itself. We have improved them significantly, but the history of solar cycle 25 is a reminder that our understanding of solar behavior has limits we do not fully comprehend, and that when the sun decides to behave differently, it does not wait for our forecast to catch up. The very same math that allows us to predict the weather in space is telling us that our immediate future is highly volatile. The sun is not settling down, it is ramping up. There is a philosophical weight to all of this. Our entire modern civilization, with its digital networks, fragile power grids, and ambitions of deep space travel, has only been allowed to exist because our star has granted us a brief, temporary window of quiet. We built our society on the assumption of a gentle sun, but the history of solar cycle 25 proves that assumption was always flawed. We are a technology-dependent species living next to an unpredictable nuclear furnace, and the record of that furnace contains events that would end the world we have built. We cannot control the sun. We cannot build a shield large enough to protect the Earth. All we can do is watch the dark spots on the solar surface twist and contort, knowing that eventually the tension will snap and the fire will come. The sleeping giant is awake, and the next time it fires a superflare, we might not be on the wrong side of the calendar. Thanks for watching, and I'll see you in the next one.